Okay, we try to solve this problem. In this problem, we are asked to find the value of this RD to keep the MOSFET at verge of saturation, even though the value of RD is given as 2.2K. So we are asked to find what is the value of RD so that MOSFET is at verge of saturation. So let us have all these parameters written there. So as per this circuit, so we have this is the circuit what I have. This is VDD, which is equal to 1.8 volt, and this is RD to be found. So the W by L of this is given as 25, and we have been given a VGS of 0.7 volt. So the device parameters KP is 200 microampere per volt square for NMOS transistor, and the threshold voltage is 0.4 volt. We are asked to find the value of RD to keep the MOSFET at verge of saturation. Now we all know that MOSFET has got this type of output characteristics. This is the value of VDS and this is ID. Let me just make it so, and we know that, so this is the value of 0 VDS, and then as the value of VDS increases, current increases. So this is the linear region. So this region of operation of the MOSFET is linear, and here it is saturation, where the current is almost constant irrespective of the value of VDS. So we have a transition from linear to saturation region, which we call it as verge of saturation. So this is typically verge of saturation. This is for a given VGS. So this is verge of saturation, we call it as VDS sat, or overdrive voltage, which is nothing but VGS minus VTH. Now coming to this VGS, we know VGS is given as 0.7 volt, and VTO also we know, because VTH and VTO both are same. It is 0.4 volt. So naturally VGS minus VTO is equal to 0.3 volt. So VDS sat is equal to 0.3 volt. So this is one observation from the circuit diagram. So now we are asked to find the value of RD so that this MOSFET is at verge of saturation. So when I say verge of saturation, VDS, that is drain to source voltage of this N MOSFET, should be equal to VDS sat. So this is the condition where the MOSFET is at verge of saturation, which is exactly here. Now we know that this VDS should be equal to 0.3 volt, so that MOSFET at verge of saturation. How does this VDS is related to this RD? So let us obtain the expression for relationship between this VDS and RD by writing a KVL equation for this outer loop. So let us assume a current of ID flowing through the drain terminal of the MOSFET. So can we write this as voltage rise is VDD, and there is a voltage drop here. So this is the current ID flowing through this. So voltage drop is minus of ID into RD, because drop is current flowing through this resistor, which is ID, and resistor value is RD. So this is the voltage drop, and there is one more voltage drop between this terminals, which is now VDS. So again minus VDS is equal to 0. So from this I can rewrite this as VDS is equal to VDD minus ID into RD. Now we need to rewrite this equation to find the value of RD maximum, so that this becomes 0.3 volts. So we will just simply replace this VDS by VDS sat, at that time this RD will become RD max. RD max. So looking at this equation, we know that this is a constant value. This is a constant value, and ID is also constant during the saturation region. During the of course, the saturation regions go till here. So this is also constant. This is also constant. If you change the value of RD, suppose if you increase the value of RD, this whole value will increase. So which will make this value to reduce. So for a particular value of RD, this will become 0.3. We need to find at what value of RD this becomes 0.3. So that's what we are finding here. So the equation now is 0.3 is equal to 1.8 minus ID we need to find. So ID I don't know. I can find the value of ID as equal to, because since ID is in, or MOSFET is in saturation, I can use the saturation equation of the MOSFET, which is half Kp W by L VGS minus VTO whole square as my ID value. So okay, I can actually calculate the value. So is it not? So it is 0.5 into 200 exponential minus 6 into 25 is W by L value, multiplied by VGS is 0.7 minus 0.4 whole square. So that is now given by 225 microampere. So this is 225 microampere. I can substitute the same thing, 225 microampere. This is RD max. RD max. So I can use this equation as it is. 0.3 alpha equals 1.8 minus 225 exponential minus 6, that is 225 micro, multiplied by, this is an unknown parameter, alpha A. Now make it shift calculate. So I got the value of this A as, you can just put it engineering, it is 6.66. So RD max is given by 6.66 kilo ohm. 6.66 kilo ohm. So this is, suppose the value of RD is less than 6.66 kilo ohm, the voltage is more than 0.3 volt. If the value of RD is 6.66 kilo ohm, then this will be exactly 0.3 volt. If the value goes beyond this, then this VDS will goes less than 0.3. So MOSFET will go out of it, it will go into the linear region. So verge of saturation corresponds to RD is equal to 6.66 kilo ohms. So let us do a simulation to understand this. So let me go here. So let me just take, so this is an activity where we have, so now let me, so this is a mini task. So let me just take, let me just see where is that. Okay, this is question number, this is the thing, no, this is, okay, let me slightly modify this. So this is, what was W by L? It was 25, W by L is 25, now that is 10, so this should be 250 micro. So this will become a W by L of this one, and let me make this a variable. I will make it as some RVAR. This is fine. So let me save it as, okay, this as question number 1 to 1. Okay, and this is fine. So let me change the value of RVAR from, okay, I know that it was at 6.66, you will get it. Let me just vary from 2K to 10 kilo ohm, 2K to 10K in steps of maybe 100 ohm. So I am changing this value of resistor. Let me name it as RD only. I'm changing this RD, and this is 0.7. So let me do, okay, let me observe, let me just name it as VDS. So this is my VDS. I'll keep it here and I'll wire it to this. Okay, now I will run it. Okay, let me take out this. If I see this voltage VDS, see now VDS is a large voltage when the resistance is very small. So we are starting from 2K to 10K. When it is 2K, you can see the VDS is 1.33 volt, and since it is far more than 0.3, so it's in saturation region. So this, whatever value that you have on the x-axis is the resistance RD value that is being varied from 2K to 10K in steps of 100 ohm. So you are looking at what is the value of RD for which VDS becomes 300 millivolt. So let me keep moving this. So just have an eye on this. So when it becomes 300, so theoretically we found that they should be 6.66K. Let us see how much is now 6.66K or not. So we are looking at 0.3. So this is approximately 0.3. Don't you have this as 6.66 kilo ohm? So this proves that for a resistance of RD which is close to 6.66K, you have a VDS which is 300 millivolt. Suppose if the value of RD goes beyond this, can you see this is less than 300 millivolt? So MOSFET is now in linear region. So the question was, we are asked to find the value of RD to keep the MOSFET at verge of saturation. The answer now is, it is 6.66 kilo ohm. So as per this problem, as per this solution, so we just found that it should be 6.66 kilo ohm. 6.66 kilo ohm. Now we will see next problem. In the next problem, so it is similar type of problem. Now you are asked to, in this problem you are asked to find the value of W bell to keep this MOSFET at verge of saturation. Since it is again the verge of saturation, so let us see how do we, okay, now this is 0.6. Let me just copy the problem here. So now we have this. So I have a problem. Second problem is now again, but this is given as 0.6 volts. This is still as 1.81. The RD is kept at 1 kilo ohm, and this W bell we are supposed to find so that this is at verge of saturation. So we are still assuming Kp to be 200. Oh, okay, yes, sorry. So now this is what I have. Let me make this volt. So this is a circuit what I have. So this is RD1K, 0.6 is VGS. So this is 200 microampere per volt square, and I have a VTO of 0.4 volt. Again, since it is verge of saturation, so the equation now becomes VDS is equal to VDS SAT, which is equal to 0.6 minus 0.4, it is 0.2 volt. Again, as we did in the last problem, now VDD is equal to, again current flowing is ID, is equal to ID. Okay, we have ID RD plus VDS. So now I can rewrite this as VDS is equal to VDD minus ID RD. So can I now write this VDS SAT is equal to 0.2 is equal to VDD minus this ID is now because RD is kept constant, when you change the value of WBL, ID will certainly change. You are trying to find what is ID max. ID max with a RD is equal to 1 kilo. So can I now write it as 0.2 is equal to 1.8 minus what is ID? It is half Kp W by L VGS minus VTO whole square into RD. We know all the values. So I know Kp, I know VGS, I know VTO, I know RD, but only this WBL is not known. So let us use the calculator and try to find out what is that. So now when I just substitute this as 0.2, this WBL becomes WBL max. So I will just do that. 0.2 alpha equals 1.8 minus, let me just do it, 0.2 alpha equals 1.8 minus 0.5 into 200 exponential minus 6 into, this is to be found alpha A into, this is 0.2 whole square into 1 exponential 3, because RD is equal to 1k. Now shift cal. I can see WBL is coming out to be, WBL max is coming out to be 400. If WBL is 400, then MOSFET is at verge of saturation. How do we verify whether this for 400 WBL will it be in saturation or not? We can certainly do it. Taking this WBL as 400, can we actually find the value of ID? ID max is equal to half Kp W by L max into VGS minus VTO whole square. So what I'll do is, so this is 400 into 0.5 into 200 exponential minus 6 into, so is it not 0.2 whole square? So I should get 1.6 milliamperes of current as my ID. So this will be the ID max, ID that will flow when WBL is 400. If you carefully note at this, if the current flowing through this is 1.6 milliampere, if the current, this is 1.6 milliampere, then what is 1.6 milliampere into 1k? Is it not 1.6 volts? So ID into RD will become 1.6 volts. VDD is equal to 1.8 volt. Then what is VDS? Using this equation, is VDS is equal to VDD minus IDRD. Is it not 1.8 minus 1.6? Is it not equal to 0.2? Now when this ID flowing is 1.6 milliampere, when the ID flowing is 1.6 milliampere, VDS will be 0.2. So that's what we found out. So let us verify the same thing over here, the simulation. So let me open that second circuit. This is my second circuit where I'm having the W as a variable one. This length is kept at 10 micro, so that W by L, whenever the W becomes 4000, then W by L becomes 400. So now let me just delete this, let me just close that. So let me have this and do the simulation. So I'm just varying this width from 100 to 5000. So this 100 micron to 5 micron, because I know that at around 4000 micron this will come to saturation region. So that's I'm just giving this range from 100 micron to, even you can just change this to 2000 also. I can start from this 2000 micron to, if you feel okay 100 is too much, 100 is too less, so I can just do here. If I run, okay, what's it saying is effective. Okay, let me just check out what is an issue. This is fine. Okay, let me do undo here, F9. Okay, that was okay now. So if you want to change this to 2000, you can certainly do it. It's actually varying from 0.1 milli to 5 milli. So if I change the range, now it is changing from 2 milli to, that is from 2000 micron to 5000 micron. If I find the value of this VDS, see now this is the value of VDS. Now you look for where this VDS becomes VDS sat, that is 0.2. So have a look at this VDS, because okay, let me name this also as VDS. How do I name it? Go to this, type this as VDS. I will put it here. I will wire it so that I will be knowing okay which voltage I am trying to see. Now if I run it, can you see now if I just measure this voltage, is it not VDS? I will just delete this. Okay, I'll make this color as something different. Okay, now let me trace this VDS where it becomes 0.2. Just have a look at this. Is it not? Okay, it has gone below that. Now I have to look at 0.2. Can you see? Are you almost there? You can see this is almost 4000 micro. 4 milli is nothing but 4000 micro. So it is almost 200 millivolt. So what we actually saw here is for a value of W bell of 400. So when L is equal to 10 micrometer, when W by L is 400, then what is W? Then it is 10 micro into 400, which is nothing but 4000 micrometer. So this is the value of W max at which MOSFET is at verge of saturation. So that's what is this showing you. Okay, fine. So let us move on to the next. So in this, okay, we are asked to find the value of R2 to keep the MOSFET at verge of saturation. So we are asked to find the value of R2 to keep the MOSFET at verge of saturation. Let me just copy that question. I'm just copying that question here. The question says, let me write it. This is again 1.8 volt grounded. So this is W by L is 40 given. This is given as 1.5K. This is R1. This is R2. This is given as 200K. This is so and so. We are asked to find R2 to keep the MOSFET at verge of saturation. MOSFET at verge of saturation. Now again, when it is verge of saturation, VDS should be equal to VDS sat. So that is the key. Okay, now let me just do this. VDS is equal to VDS sat, which is equal to VGS minus VTH. But here, what is VGS? Because I don't have a VGS directly given here. VGS is actually equal to VDD into R2 by R1 plus R2. So first, let me find out what is the value of VGS required. So how do I find the value of VGS now? So shall I write what are the other things that are given here? Okay, now I can actually find out VDD. Okay, let us write the KVL here. This is minus plus voltage rise is VDD. Again a voltage drop ID, it is minus ID into, this is the resistance RD, ID RD, and there is again a voltage drop. This is VDS minus VDS is equal to 0. So VDS becomes VDD minus ID RD. So what is VDS? It's actually VDS sat now. VDS sat is equal to VDD minus ID RD. So let me rewrite this. VDS sat, which is nothing but VGS minus VTO, is equal to VDD minus what is ID? It is half KP W by L VGS minus VTO whole square into RD. So in this expression, we know all the parameters except VGS. I know VTO, which is 0.4. I know VDD 1.8. I know what is Kp, which is 200 microampere per whole square. I know W by L is 40. I don't know this VGS, so this is the VGS which is unknown, and I know this. So now let us feed into Calci and find the value of VGS. So now you can open the parenthesis. VGS is a parameter which is unknown. Let me just redo it. So open the parenthesis, alpha A minus 0.4, close the parenthesis, alpha equals, now you have 1.8 minus 0.5 into 200 exponential minus 6 into 40, because that's what your W L, into alpha A minus 0.4 whole square into 1.5 exponential 3. Now do shift calculate, I'll get the value of VGS. So I'm getting the value of VGS as, VGS is coming out to be 0.87 volt. Since it's a quadratic equation, I'll get one more value of VGS. Let me find that also. To find that other value, let me equate these to some negative number. Again equals, shift calculate. Oh, you got one more value which is minus 0.237 volt. Since the mathematical equation, since it is quadratic mathematical equation, I have two values of VGS, whereas electrically this is not a possible solution because VGS cannot be negative, so I have to consider this as my VGS. So now what is VGS? VGS is this. So this is equal to 0.87 is equal to 1.8 R2. I know what is R1. So is it not 200K plus again R2? Now solve for R2. Again, when I say solve for R2, no need to do any mathematical stuff there. Just feed into equation as it is. So is it not 0.87 alpha equals, open the parenthesis, 1.8 into alpha A divided by 200 exponential 3 plus alpha A. Wherever R2 is there, I am just replacing by alpha A. Close the parenthesis, shift calculate. You can see you got the value of R2. You can put it ENG. So it is 187.09 kilo ohm. So this is the value of R2 for which MOSFET will be at verge of saturation, because as the value of R2 changes, my VGS change. As my VGS changes, my ID changes. ID change will make my VDS to change. So you can see this, if my ID changes, as my R2 change, which will change VGS. If ID changes, my VDS changes, which will make the MOSFET to be either in saturation or linear region. So let us do this, verify that in simulation. This is question number 3. You have the same thing here. So let me delete. Okay, save this and then take out. See now, do you have RD as 1.5K? Do you have WL as 40? And do you have this as 200K and this as variable one? I am varying it from 100K to 200K because I know that it will happen at 187 kilo ohm. Now with this dot step param, I can see the result. You can see now the value of R2 is varied from 100K to 200K. How did I choose these ranges? Because it was found in the calculation that this comes out to be 187. So it's a better choice to make sure that 187 comes within the range. Okay, let me also just name this output as VDS so that you are just seeing VDS. Okay, this is VDS. Let me wire this also. I'm wiring it. Done. Okay, now I will run it. And when I see this, I'm seeing VDS. So now let us look for VDS, which is now how do we know that, okay, what is VDS and VDS at 187? To verify this, so let me also take VGS. Let me also take VGS here. So let me name this as VGS, so that when the difference becomes 0.4, that becomes my VDS at. This is VGS. So this is VGS. Fine. Okay. Let me connect this to this. Now we know that. Suppose you just come back here, because in this I am unable to make out which is my what is the value of VDS at saturation. Of course, what is the value of VGS here? Sorry, here. What is the value of VGS? It is 0.87. So what is VDS sat now? So VGS is 0.87. Then what is VDS sat? Are you now looking at VGS minus VTO, which is 0.87 minus 0.4? Are you looking at 0.47 volt? So let us verify. At R2 is equal to 187K, your VGS should be 0.87 and VDS should be 0.47. So let us verify both of them. So I'm here. So this is VDS. Let me also see what is this. Let me run it again. Let me see this. Now I'm just seeing this. This is VDS and other one is VGS. Can you see this cursor one? This is my cursor one. This is actually showing VGS. Can you see here? This is cursor one VGS. So look at this voltage as 0.87, because this is my 0.87 VGS and this is 0.47. So let me just make this as 0.87. Are you there at 0.87 somewhere here? Oh, you're almost there. Okay. This is your point. Can you see the resistance? So on the x-axis, what you have is the resistance, 187 kilo ohm. So at the same time, so the VDS should be 0.47, because let me move this VDS. Can you see now VDS is keep reducing, and when this is equal to 187, that is when this also equal to that, then this will become 470. Are you there at 470? Can you see there? You're there at almost. See here? This is almost 470 kilo ohms. So let me just make it somewhere here. This you are looking at 470. Can you see? This is 470 and the resistance is almost 187K. So this way we can able to verify whenever this is, because over here we found that when the value of what R2 is 187K, so VGS is 0.87 whereas VDS is 0.47. Okay, thank you. We will see the further problems in the coming videos.